This is day 2 of lesson 403, exponential functions and models. Today is a work day for your teachers, so there are no live classes. This will just be a short recording to kind of walk you through this second part of the lesson, and we'll go through some of your practice together as well. Your learning target for today is right here. It's the one in the middle. You're going to be using key features of graphs and tables to model relationships between two quantities. We've talked about exponential growth and decay before, but here's just a recap of those ideas. Exponential growth is when you have a function where the dependent variable is increasing by the exact same factor over each unit of time. That means you're multiplying by the same thing over and over and over again, and the values are getting larger as you go. The base of an exponential growth function is greater than 1, because you're keeping more than 100% of your value each time. That's why the base has to be greater than 1. Exponential decay is the other version. That's going to be a function where your dependent variable is decreasing by the same factor over each unit of time. So we're multiplying by the same thing over and over and over again. That makes it exponential, but we're multiplying by something that's letting us keep less than 100% of our value each time. That means that our base has to be less than 100% or less than 1. But we do also need to be greater than 0, because if you are at 0% of your value or a negative percent of your value, that does not make an exponential function make sense. Our base is just going to be a number that's between 0 and 1 to show that we're decreasing over time, keeping less than 100% of our value. The graph of an exponential function is a curvy line, and we can either describe those lines as a growth or decay function. I have them both here on the screen for you to compare. The growth function is on the left. This is when the base of your exponential expression is greater than 1. Here are some examples. We could have f of x equals 0.01 times 2 to the power of x. And then the other function here is 0.5 times 1.04 to the power of x. Both of the base values, 2 and 1.04, are greater than 1. That means that both of those functions would show growth, because we are growing by keeping more than 100% of our value each time we evaluate the function. The graph that's down here does not necessarily go to either one of those written functions, but this is just the picture of what growth looks like. It increases from left to right as you read the graph. Exponential decay is the opposite of all of that. It happens when your graph goes down from left to right as you read it, and the base of that exponential expression is between 0 and 1. Both of these functions are showing decay. We have 2 times 0.5 to the power of x and 100 times 0.97 to the power of x. Notice that both of those base values are less than 1. They are greater than 0, but they are less than 1. The example here at the top, 0.5, means we're only keeping 50% of our value each time, and the 0.97 means that we're only keeping 97% of our value each time. So we're losing 50% on the top one and losing 3% on the bottom one. Some of the other key features of an exponential function would be the domain, the range, and the y-intercept. Your domain is going to be all real numbers, because your x value can be anything. It can be a negative, it can be a positive, and you could go think of any number that you could possibly think of for your x value, and that would be fine. So your domain is all real numbers. Your range for these exponential functions is going to be greater than 0. Notice that in both of these graphs, the y values are all positive. They are all greater than 0. And our y-intercept is usually 1. It's going to depend on the function, of course, but your y-intercept is the initial value. Yesterday, we talked about that being the p-value in our equation that we took a look at for things like compound interest. Notice, please, that these features will change based on your real-world situations. Your domain and your range can be different depending on what a word problem is setting up for you. It will have to make real-world sense for the problem. Let's take a look at some examples. In the function f of x equals 3 times 4 to the power of x, I want to figure out if that is growth or decay. I'm going to go look at the base of my function to figure that out. The base here is a 4. Since that is greater than 1, this is going to be showing growth over time. The domain is then going to be all real numbers. X can be whatever it wants to be. The range is all of my positive values of y. You can see that here in the graph. And then the y-intercept for this particular graph would be the point 0, 3. If you didn't have the graph, you could still find the y-intercept by putting a 0 in the place of x. I'll go ahead and do that for you here. If I do 3 times 4 to the power of 0, I get 3 times 1, which is 3. Plugging in a 0 in the place of x gave me a final answer of 3. That would be my y-intercept. Take a look at another example. We have the amount of weeds in a park that are decreasing according to this function f of x equals 250 times 0.87 to the power of x, where x is the number of weeks since volunteers started cleaning the park. The volunteers are only scheduled to work for 10 weeks. Let's figure out if this is growth or decay and find our key features. To find if we are growing or decaying, we're going to take a look at the base of the function. The base is this number here, 0.87. Since 0.87 is less than 1, that means I have a decay function. And I also have it graphed here. You can use Desmos to graph these functions if you'd like. The domain is going to be integers, where x is between 0 and 10. So notice in this one that our domain is not all real numbers. That's because it is a real-world situation. We are only using the whole numbers because x is standing for the number of weeks. So we want like 0 weeks, 1 week, 2 weeks, 3 weeks, 4 weeks, 5 weeks, all the way up to 10 weeks. That is how many values of x make sense for this problem. We wouldn't talk about like 0.83 weeks. We wouldn't do that. It would be a whole amount, and so that's why we're just using the integer values between 0 and 10. The range for this function would be all of the output values. And if I go between 0 and 10 for my x values, you can see that I kind of skipped some places on my table here and jumped from 3 down to 10 just to show you where it ended. But our integers for the range value are going to stop at 62 here on the low end and then up to 250 on the high end. So integers are acceptable here. We're not talking about decimal or fraction values of weeds because that doesn't make sense. You either pull the weed out or you don't. It's a whole number. The y-intercept would be the initial amount or the starting value of the number of weeds. You can see it here on the graph that the 0.0250 is our y-intercept, but you can also find that by plugging a 0 into the original function and finding that initial value. Go ahead and pause and try this one. We'll show the answer in just a minute. You can also pause and try this one, and I'll show the answer in just a minute. Here are the solutions to those two problems. The first one said the average price for a new car is $30,000. Each year, the value of that car decreases by 15%. The answer to that one was decay because we are decreasing by 15%, so we're losing value. To write the function, we put the starting amount here in front of the parentheses, and then we do 1 for 100%. This problem was decreasing by 15%, so I will subtract 15% from my 100%, and I'm raising that to the power of x. If you wanted to simplify that function, you could. I'll go ahead and write that for you. Here's the simplified function. I just went ahead and simplified inside those parentheses. 1 minus 0.15 is 0.85, which shows that we're keeping 85% of the value of the car. That makes sense because we lost 15%, we're keeping 85%. The domain for this one would be x is greater than or equal to 0 because x is standing for the number of years. Years cannot be negative. And then the range would be all of the possible values of the car. We are going to be going between $0, that would be the lowest amount that the car could get down to, and then it has to be underneath $30,000 of value. Have an extra 0 in that answer. There we go. And the y-intercept would be the initial amount of the problem. So after 0 years have gone by, the car is still worth $30,000. The second example was about the king crabs. Initially, there are 23 crabs, and the population is growing by 8% each year. So to figure out if that was growth or decay, just look for some of those keywords. We are growing. Your function is written here with the initial value in the front of the parentheses, and then the inside parentheses shows us how we're growing. I'm starting with 100% of my population, and I'm growing by an extra 8%. If you wanted to simplify this function, it would look like this. 1.08 inside the parentheses means we're essentially keeping 108% of our population, which is greater than what we started with. The domain here would be x is greater than or equal to 0 because the number of years has to be positive. And our range would be all of our possible numbers of crabs. So my y values, my output values have to be greater than or equal to 23. Since we're growing, 23 will be the lowest number of crabs that we could possibly have. The y-intercept for this problem will be the starting amount. After 0 years have gone by, there are 23 crabs in the population. To practice this topic, I want you to go ahead and get an IXL and work on this for a little while. You've got two different situations here. You've got x3, which is the domain and range of an exponential function by looking at the graph. And then x4 is the domain and range of exponential functions by looking at the equation. I'll go ahead and do an example of each of those to kind of show you what it's like. I'm signed in here to the x3 session as a teacher view, so mine might look a little bit different than yours. It's asking me here for the domain of the function. The domain is my possible x values. The majority of the time, it's going to be all real numbers unless you have a word problem. So I'm going to just take a look at my graph here. I don't see anything strange going on with it, so I will say that x could be all real numbers. Let's try another one. This one is asking for the range of the function. Most of the time, your range is going to be anything that's greater than 0. You can't be exactly equal to 0 because this is called an asymptote right here. You're never going to touch this orange dotted line, even though it looks like you do right here. It just gets really close to it. It does not actually touch or cross it. All my y values are positive. They're greater than 0. So it would be this first option here. And so again, you just keep going with domain and range there. Let me go ahead and pull up the other session that you can try, which is looking at the equations to figure out if you have a domain and range. For this one, you're given the equation instead of the graph. Y equals 5 to the power of x. Most of the time, again, your domain will be all real numbers unless you have a word problem, because here my x value can be anything that it wants to be. The range goes to your possible y values or your output. We talked about before how those are going to be your positive values because you have an asymptote at the 0 level. So all of my y values are going to be greater than 0 for that one.